Hello and welcome to RF Design Tutorials. This is tutorial 15 on graphical load pull and XdB compression based load pull analysis. Before we start, subscribe to my channel. Once you subscribe, don't forget to click on the bell icon to enable all the notifications. And after you watch the video, give it a thumbs up and share it with your friends and colleagues who may be interested in watching similar tutorial. Now, before we start to this tutorial, make sure you have already watched tutorial 13 and 14 so that you have the basic fundamental concepts in place because we are going to talk about little more advanced thing in this tutorial. Now, I would like to say special thanks to my friend and colleague, Andy Howard. He is a old-timer in HP Agilent Keysight, and he specializes in various simulation techniques for power amplifier analysis, load pull, envelope tracking, and so on. He's very active on LinkedIn. If you want to follow him on LinkedIn, I have provided his profile ID here. Feel free to follow him, and you will get a lot of useful information coming from him. So part one of this video will talk about how do we select loads required for our load pull analysis in a graphical manner rather than thinking about the potential zone and the area on which we want to run. So this will simplify the whole load pull running experience very nice, and you would be able to figure out where exactly would you like to run the load pull, and you will see various tricks we have in store for you. In part two of this video, we will talk about techniques. How can you avoid going into deep compression level while performing load pull? Remember in the last tutorial, we talked about the need to do a power sweep analysis to see how much compression level you are operating on while you are getting your desired output power. But sometime during that analysis, depending upon which load point you are analyzing, some of the load points can really push your device into deep compression, and that's where we might see convergence failure due to the nonlinear model of the device being pushed into such corner that it cannot produce a steady state response, causing the convergence failure during harmonic balance analysis, which we use during load pull. So let's go step by step. Let's talk about how can you perform a load pull simulation using the graphical area selection and nice utility. Now, all these techniques which I'm going to present can be downloaded from the Knowledge Center website. So look at the links I have provided in the description box. Using the first link, you would be able to reach to this load pull simulation, which is like a landing page. And here you do have a lot of other useful links provided for you to get the right idea. The second link will give you access to the workspace where you can play with various templates available to select the loads graphically, and then based on those loads run your load pull analysis. Again, depending upon what ADS version you are using, you can get the right workspace and the associated PDF document explaining the detail about the templates available. In the second part of this video, we will talk about this example, and by clicking on the third link in the description box, you can reach to this place, and that's where you can download the last update, which was November 5th. You have an ADS workspace as well as a PDF document explaining the concepts or the templates which you have in the workspace provided. All right, with this short introduction, let's go to ADS. And so what I have done using those two workspaces of graphical, load selection and XdB compression file, I only, included few of those templates in this to explain that in this video. So when you download the workspace, unarchive and start using it, you will see plenty of templates available, but I have selected some of them. So first, let's talk about graphical load pull. Now there are various data display templates available for you to select the desired, desired region in the overall smith chart of various shapes. So the first one I'm going to use here is basically allows you to select a circular region. So as you can see in this template, you have some instructions given to you how to use, but it's very simple. So basically, you have the first selection here, whether you want to use markers to choose the respective center of these circles or not. If you set it to 0, then you can enter these parameter here, z center 1 value, z center 2 value, to accordingly position these two circles. Now, in case you only want to select points with one circle, on the right hand side, you have a couple of sliders. And if you don't want to use this circle, you can set the radius to 0 and probably set the number of points in that circle to 0. So with these two, you can make your selection only with the one circle and you can avoid the second point. Now this circle and the area around the Smith chart, you can move the slider up and down depending upon how much zone you want. And also you can pick up this marker and place it anywhere in the Smith chart. In case you place the marker or the center, which is very close to the edge of a Smith chart, and the circumference is falling outside a Smith chart, the template inbuilt has intelligence to neglect the points which fall outside a Smith chart. Because realistically speaking, as you know, you have to be within Smith chart to select the right load point. So all these intelligence have been inbuilt into the template. Now, once you are able to select, so let me switch on the number of points to 50 within the circle, and let's give our circle some radius here. Now, let's say if I have these two circles and these circles can cross each other, for example, like this. So all the dots which you see inside can be controlled by this index point. If you want to have, 100 points within that circle, you can change it to 100. And accordingly, those many selection points will be available. So let me try doing this. So let me put both of these into 100, but I will shift this circle so that it slightly goes outside the Smith chart, resulting in some points being denied as a valid row point for our load pull. Now, once you made your selection, at the bottom here, you can see you can create your own file name. For example, default file name is load underscore fundamental.mdf. You can give your own file name. And by activating this equation here, by simple right clicking, toggle activation, now this file will be written inside your workspace folder. So let's go into a workspace folder and find this file. So the easiest way to go to workspace folder is simple right click, explore in file system, and it will take you to the workspace folder. Now in this folder, you can see there are plenty of files. And if you arrange the file by date modified, you can see the file which we just created just now. Now, if you open that file in any notepad editor, it's very simple syntax here. So you have a begin header, and then you basically in the first column, you have the load index, and these are the index of those points which we selected, and the associated row real and row imaginary. And if you scroll through the file, you can see we have created 179 points, which were valid reflection coefficient point. Now in our load pull analysis, these are the load points which we really want to use. Now once you know the file, let's go back and see how can we read the information in this file to run load pull. So here is a schematic template, and if I double click on the template, is a normal load pull analysis where we do have a parameter sweep defined, like I showed you in one of the earlier tutorials. And in this parameter, we are sweeping the load index starting from 0 going to the total number of rows minus 1, which is basically till the last row. And then we do have a harmonic balance, which is having a parameter sweep for the power, the input source power. Now, where is the load index coming from and how this load pull tuner is getting the required impedance point? Well, here in ADS, if you are already aware, we have a concept called DAC or data access component, using which you can open any file and read in the data from that file. So here we need to browse to the right file, which we just created. So let's double click on this DAC, click on browse, and looking at MDIF file, and this is the load fundamental file which we just created. Select that file, click open, and now click apply. And now you can see this component is directing to this file. Now, once we have that file, we are simply reading the load index information. And once we point to a particular load index, we are reading from this file row real and row imaginary. These were the names of those headers, containing our load reflection coefficient point. And like in the earlier video, we are making a complex impedance, which is load underscore fundamental, and that's what being passed to this load pull tuner here. Now, once we have all the right data, we can go ahead and run simulation. Now it will open the file, it will read the index and keep on passing the load reflection coefficients to our simulator. And as you can see here, we are running around 180 harmonic balance simulation, so resulting in overall 180, load pull simulation. Now, along with this circular region, so while the simulation finishes, it takes few seconds to run an open data display. There are other templates also available, such as to select a pie shape or select two pie shapes to create your own custom profile, or to create a spiral looking area, or what we call as Archimedes spiral. So all these useful templates are available. So before we go to this template, so here we can see the response. And if we zoom into the center Smith chart, you can see the load reflection points where we analyzed our transistor in terms of load pull. And we can see the PAE contours in the center point. And these pink points or purple points are basically where your desired power is not satisfied. And this is what we talked about during the last video as well. And using the slider, you can select what's your desired output power. And depending upon what level of power you set, accordingly the contours will change, and the location where your output power cannot be met will be highlighted on the Smith chart, as you can see here. Right, so rest of the plots are very normal like we saw earlier. So this is the load which gives you minimum gain compression, which in the current case is around 1 dB, the maximum gain compression point, which is 7 dB, and so on. So rest of the data is self-explanatory. Now, notice when we are sweeping these load points and looking at the gain compression here, you can see we are pushing our transistor to 7 dB gain compression, and sometimes it can be even 10 dB or more. And those are the typical causes when you use any vendor transistor library component, you start to see the convergence error. And in the second part of video, we will learn how to avoid doing all those deep compression base simulation to avoid any of those convergence issue. But this is a very simple concept. So just to quickly revise, we open the template to select the load graphically. Once we were satisfied with the area or the type of loads we want, we activated this utility to write out the file. And then we simply switched on the schematic template, browse to the right file, and we ran the simulation. So this template is very, very useful to do so. Now, before we go on to second topic, just a quick thing I want to show you. So with the pie shape template in data display, you can notice again, choose marker to select corners is activated. And if I move these markers, you can see those pie region will be created, and accordingly the load points will be calculated. And this makes it completely arbitrary. You can go anywhere in the Smith chart, create your load points, and like earlier, define your file name, activate this equation, create a file based on these reflection coefficient, and simply use it in your load pull simulation template. So this is with one pi region. And there is another template where you can do even better things, which is 2 pi. And again, here you can see I have two corners marked with red and green. And when you select these marker corner points, you can come up with a totally arbitrary looking regions in the Smith chart to perform your load pull. And rest of the concept remain the same. At the bottom, you define your file name, activate to write out the file, and then use it for your simulation. Now, another interesting thing, the last template here is like a spiral. So once you create your circle, circular points, for example, instead of using all these circle points after you have done, and if I change the page, you can notice the spiral or the valid rows to create this spiral, kind of network. So when we write out the file, the load coefficients falling on this spiral point only will be the ones which will be written and used in our load pull analysis. Isn't that all cool to give you the flexibility you were looking for to perform load pull, right? So thanks to all the good work done by my colleague Andy Howard, go ahead and download this workspace from our knowledge center and try to use it the way you want. All right, so now let's go to part two. How can we avoid deep compression while performing the load pull? Well, there is a template available on the Knowledge Center, which you could go ahead and download. And this is what I'm going to show you here. So this schematic template allows you to insert your own device or amplifier to be pulled. It could be your Cree device or any other vendor device like we used earlier. And there are two parts to this demo, and I will demo both parts. So in first part, like we do classical load pull, we define the radius of the region, we define the Z center or the row center to select the zone in a Smith chart, and then run simulation by selecting the proper terminating condition for second harmonic, third harmonic, or input fundamental power or input fundamental impedance. We select the input power, which is being fed to this transistor, and how much XdB target we are looking at. So based on this target, ADS has a nice capability where you can do a programmable optimization. So the template which you see here is basically programmable optimization. And this parameter sweep is setting the optimization sequence. So we are going into various stages, not like a blind optimization to give me, that dB compression point or that amount of gain, which often results in a very inefficient and a very long simulation. So this parameter sweep is going to run HP analysis first so that it knows the notional response. And then it goes and assigns data, find XdB gain compression point, and so on and so forth. So it goes and performs these simulations in a sequence. Now, in a normal sense, when you deal with ADS optimization, if you have one optimization controller and multiple goals on your schematic, usually that is sufficient, and that's like a regular optimization. But in order to make it like a programmable optimization, you can see what is being done here. Not that you have to do it. All this template will mean you have everything to just plug in your transistor, define your frequency, voltage condition, input power, and the XdB compression point, and it will be up and running. But just to give you a concept of what's going on behind the scene and not forcing you to do anything manually. So here in one optimization controller, by default in areas when you optimize your circuit, this option is already set. That means one controller will take care of all the goals which you have. But this is not what we want here. And in a moment, you will understand why. So one controller here is only taking care of one goal, which you can see the name here, assignment goal. Similarly, when we are going to do an XdB compression point in a coarse power sweep, that optimization controller is only taking care of this goal. And this one, which is fine sweep of power to get precisely to that XdB point, is only going to take care of this goal. So all this intelligence programmable optimization feature is already implemented into this schematic, because this is something which needs a lot of expertise with ADS to set it up. And that's where Andy's contribution is so precious for all the designers. So once we have set up all these templates, we run and we simply click on optimize to go ahead and do the analysis we are looking at. But before we go and hit optimize, I just wanted to show you what is the concept used behind the scene. How are we able to avoid deep compression point using this technique? So let's go back to the slide here, right? So step number one, before you start using the sequential optimization template, obviously you have already run your nominal load pull analysis. You know the region of the Smith chart where you are going to get your desired power, and you have already run the previous analysis. So you really know how much input power you really need to get your desired gain and the output power you are looking at. So that's your starting point. So in this case, this is my available source power where I'm getting a certain amount of gain and a certain amount of output power. Now, even if you are off, you are somewhere here, doesn't matter. This template will take care of that. But closer you are to the reality, faster it will, perform and give you the result. Now, once you know your starting point, the next step this template does, it will step through the input power and it will keep increasing the input power till you achieve your desired XdB compression. And usually in a gallium nitride kind of amplifiers, you keep it like 3 dB, and that's what you just saw in a schematic template I showed you. 3 dB. So it will stop at that point where your gain is dropping by 3 dB, and it will, even if your amplifier has a gain expansion, it has an intelligence inbuilt to pick the maximum gain point and from there calculate the 3 dB compression, not from the linear gain point. So all those things have been already included in the schematic template I showed you. So once you are able to achieve the 3 dB compression point to get a nice gain versus input power curve, it basically backs off that power by certain amount, let's say 25 dB, for example, and it runs the whole sweep again and only stopping the sweep up to this point here. So essentially what happens behind the scene, for every load reflection point, you only get this thick part of the curve, which typically stops at 3 dB or 1 dB compression point, whatever you have mentioned. So using this technique, you can avoid this part of the curve, which is high compression, and that's where you get convergence issue. So that's what goes behind the scene. So let's see how all this thing are put into action in the schematic template. So let's go back to the schematic template. I just showed you what will these guys do, explained in the PPT. Now only thing I need to do is just hit this optimization button, and the sequence of optimization starts finding for every load point, because you can see we are sweeping the load tuner here. So for every load reflection coefficient point, it is going and finding the XdB compression point related, amount of gain and so on, so that we don't, go in and push into deeper compression zone. Now, while that is working, and now we will have data display coming up in few seconds. And as soon as we do that, I will show you the same technique using the file based load pull, which we just talked about using graphical selection. Now, once the data display comes up here, you can see three columns basically. The red column has all the statistics you need for the maximum PAE point. You can see 65% PAE, but at that point, the output power is not so great. The blue is the best output power, but not necessarily meaning the maximum efficiency and all the statistics associated. And then the black one is the statistics based on the marker M1. And that marker M1 is basically here. And that's the region of the Smith chart where we performed the load pull analysis. On the right hand side, you will see three curves. Again, the same color notation. Red is the maximum PAE, blue is the maximum power, and black is with respect to the marker location. And here is your gain versus output power, or power delivered. Again, the same color coding. Now, once we start changing this marker location, notice what happens to the black curve there. So if you change the marker location, you can select the various traces, and also this readout will get updated so that you can know the right statistics. Rest of the things as usual in the previous data display template in order to select the right contour, resolution and so on. On the right hand bottom side, this graph is not populated because they are plotting the intrinsic voltage and current waveform. Now, depending upon which transistor model you are using, it may or may not give you those information. So in the earlier tutorial, I used a Cree device, and in that Cree device, we had this information plotted out. So if you're using that device, then these graphs will automatically populate for you. But in this example, we are using a generic MOSFET, which is not having that information. Right, so this is how we run a classical, kind of load pull uh, by selecting our own region and Smith chart. Now, let me just quickly show you same template in the example workspace which you will download, which has with graphical load XdB back off sweep. BO is back off sweep. So if I double click and open a schematic, rest everything here is same. It's just that now we are reading the file where we have selected our loads based on the region we want using graphical technique, which I just explained earlier in this video. And rest of the process is pretty similar. We go ahead and run optimization. And again, not to forget, you set your input available source power, which is your nominal condition, and then the XdB target, which you are looking to achieve 3 dB, 5 dB, 1 dB, and so on. Now, once the optimization is complete, again, the similar data display will appear, giving you all the statistics which you need. So again, just to remind you, the workspaces which you will download will have a lot of other information, plenty of templates for you to play with. So feel free to explore all of them one by one. And every workspace which you unarchive will have a PDF document explaining all the key snapshots and key steps which you need to use. So here is a data display. As you can see, we have the same looking curves plotted here. The only difference here at the bottom, you can notice we are using 2 pi templates. So here is 1 pi region and there is another pi region there. And those coefficients were written to file and then used inside our load pull analysis. So this DAC is a wonderful feature within ADS, and I will have few tutorials in coming weeks on how to use this DAC, because using this DAC you can do wonderful things inside ADS software to read in any customized file with any custom information and then use that into variety of applications in your simulation. But for the time being, if you want to know more about DAC, double click on this DAC component, click on the help, and ADS documentation has a lot of information and variety of things which you can do with this DAC component. And it also uses different use cases to explain the whole working of the stack. But again, if you don't understand it, don't worry. We always have a tutorial video coming your way. All right, so that's what I wanted to cover in this tutorial. Thanks a lot for your attention. Hope you like the content presented, and these techniques will be very useful for your power amplifier design work. And don't forget to give it a thumbs up and share it with your friends and colleagues, and watch on the description box below and click on the links. If you are a supported Keysight customer having Knowledge Center account, you would be able to download all these workspaces and examples. And again, at the end, special thanks to my colleague Andy Howard for creating such useful materials, benefiting a lot of PA designers across the world. Thanks and have a great time designing your circuits, my friend.